Here in Chapter 9.3, we study another type of sequence and series, this one known as a geometric sequence and series. A sequence is geometric if the ratios of consecutive terms are the same. The sequence A1, A2, A3, A4, AN, is geometric if there is a number R such that A2 divided by A1 is equal to A3 divided by A2 is equal to A4 divided by A3, which is equal to any term divided by the previous term, and that is equal to R, where R does not equal 0. The number R is known as the common ratio of the geometric sequence. Okay, so a sequence, a list of numbers, is geometric if I can take one term and divide by the previous term, and if I do that for every single term in the sequence and get the same number R, then my sequence is geometric. So, for example, determine whether the following sequence is geometric. If so, find the common ratio. Well, to determine whether or not it's geometric, I need to take a term and divide by the previous term. In other words, I take the second term, 12, and I divide by 3. 12 divided by 3, that gives me 4. Then I take the third term and divide by the second term. The third term divided by the second term, that's 48 divided by 12, is equal to 4. I take the fourth term and divide by the third term, 192 divided by 48, and that gives me 4 as well. So, whenever I take one of the terms and divide by the previous term, we always get the same number. That number is 4. Therefore, yes, our sequence is geometric, and the common ratio between terms is going to be 4. R is equal to 4. Let's look at another one. 9, -6, 4, -8 thirds, ... Again, we need to take one term and divide by the previous term. That would be -6 divided by 9. Well, -6 divided by 9, that reduces into -2 thirds. I could take the third term and divide by the second term. 4 divided by -6. Well, 4 divided by -6, that turns into -2 thirds again. And finally, I could take the fourth term, -8 thirds, and divide by the third term, 4, and -8 thirds divided by 4, well, that reduces into -2 thirds as well. So we notice that we take any term and divide by the previous term, we end up with the exact same number, -2 thirds. If we end up with the exact same number, yes, our sequence is geometric, and in this case, the common ratio is equal to -2 thirds. The nth term of a geometric sequence has the form a subscript n is equal to a1 times r raised to the n minus 1, where r is the common ratio of consecutive terms of the sequence, and a1 is the first term in the sequence, assuming that n begins with 1. And that should make sense. Notice, take a look here. If I plug in 1 for n, I get r raised to the 0 power. And any non-zero number raised to the 0 power is going to be 1, which leaves me with a1 times 1, which just says a1 equals a1. All right, so r is the common ratio of consecutive terms. a1 is the first term in the sequence. Note that geometric sequences can have an exponential relationship. However, it is also possible for the terms of the sequence to alternate sign. And they have this exponential relationship because notice your variable n, the value that we are substituting in for, is located in the exponent. So for example, here I have the sequence a subscript n equals 18 times 3 halves raised to the n minus 1. Again, this is a geometric sequence. It has our geometric format, and it has this exponential relationship. Okay, the graph of this sequence shows exponential growth. Similarly, here I have a subscript n equals 18 times 2 thirds raised to the n minus 1. Well, this sequence displays exponential decay. All right, so geometric sequences can have an exponential relationship. However, let's look at two other examples here. A subscript n equals 18 times negative 3 halves raised to the n minus 1. Notice in this case that the common ratio r is negative. And anytime the common ratio is negative, the terms of your sequence will alternate sign. Notice that the outputs change from being positive to negative, positive to negative, positive to negative, positive to negative, positive to negative. Okay, and similarly here I have a subscript n equals 18 times negative 2/3 raised to the n minus 1. Again, the common ratio here is negative, which causes the terms of the sequence to alternate signs, changing from positive to negative. So let's do a few examples here where we come up with expressions for the nth term of a geometric sequence. Here we have the sequence 3, 36, 432, comma, dot, dot, dot. Because we are writing an equation for the nth term of a geometric sequence, we need to use the proper formula. A geometric sequence can always be expressed as a subscript n equals a1 r raised to the n minus 1. Now, to complete this expression, we need to know a1 and we need to know r. Those are the values that we need to substitute in for. Again, n is your variable that we plug in for. We want to keep those n's. A subscript n is our output. We want to keep a subscript n. So we need to find a1 and we need to know r. Well, the nice thing about this list here is that we actually have a1. a1 is just the first term in the sequence. And the first term in the sequence is 3. Now, we need to figure out what r is. Well, r is our common ratio between terms. And to find the common ratio, we take one term and divide by the previous term. In other words, we take 36 and divide by 3, or 432 divided by 36. Both of those will give us the exact same value if our sequence is geometric, which it is. And here we get r is equal to 12. Now that we have a1 and r, we can substitute those into our equation. We get a subscript n is equal to 3 times 12 raised to the n minus 1 power. And again, we can check our work. If we have found the correct expression, we should be able to verify the given information. The first term is 3. That means if I plug in 1, I have to get out 3, which I do. The second term is 36. If I plug in 2, I have to get out 36, which is also true. The third term is 432. That means if I plug in 3 for n, I get out 432, which I most certainly do. Let's look at a couple others. Write an expression for the nth term of the geometric sequence. Now, in this case, we are not given the first few terms of the sequence, but rather we just have the second term as being 12 and the fifth term as being 3/16. Well, we know that this is a geometric sequence. Therefore, our expression must follow our formula for the geometric sequence. A subscript n equals a1r raised to the n minus 1. Well, let's think about what this given information means. A2 equals 12. This means that the second term of the sequence is 12, that when we plug in 2 for n, we must get out 12. If I plug in 2 for n, it has to equal 12. In other words, 12 equals a1 times r raised to the 2 minus 1. Similarly, the fifth term of the sequence is 3/16. This means that when we plug in 5 for n, we must get out 3/16. So I plug in 5 for n, I set it equal to 3/16. 3/16 is equal to a1 times r raised to the 5 minus 1. And what did we just generate here, fellas? Well, a system of equations. Now, we want to solve this system using substitution, okay? We cannot add or subtract our equations here to eliminate a variable, so we're going to have to solve using substitution. Isolate one of the unknowns, right? The easiest unknown to isolate here is going to be a1. How do we isolate a1? Well, we divide both sides of the equation by r. Notice that 2 minus 1 actually gives me a 1 in the exponent. So we have a1 is equal to 12 over r. I can now substitute that into my second equation for a1 right here. That gives me 3 over 16 is equal to 12 over r times r to the fourth power. Notice we get r to the fourth because 5 minus 1 simplifies into 4. All right, so let's do a little bit of algebra now. Notice I have r to the fourth, and I am dividing by r. Whenever we divide exponential quantities with like bases, we subtract the exponents. This is 4. The exponent here is a 1. If I have r to the fourth divided by r to the first, that leaves me with an r to the third power. In other words, 3 over 16 is equal to 12r cubed. So our next step in solving for r, isolating r, is to divide both sides of the equation by 12. Undo this multiplication. Dividing both sides by 12 gives us 1 over 64 is equal to r cubed. And now to solve for r, all we have to do is take the cubed root of both sides of the equation. Now, as you do this, especially in your calculator, I think cube roots are often easiest to do by plugging in as exponents. Remember, taking a cubed root is the same thing as raising to the 1/3 power. So if I raise the right-hand side to the 1/3 power, and I raise the left-hand side to the 1/3 power, that will allow me to solve for r. Notice, exponents raised to exponents, we multiply them. 3 times 1/3 would give me r to the first. That's why we end up with r. So we plug this into our calculator. 1 over 64 raised to the 1/3 power. We get r is equal to 1/4. There is our common ratio. And now that we know r, we can back substitute it into this equation right here to solve for a1. a1 is equal to 12 divided by 1/4. Well, dividing by a fourth is the same as multiplying by 4. And we get a1 is equal to 48. Now that we know a1 and r, all we have to do is plug them into our form for our geometric sequence. A subscript n equals 48 times 1/4 raised to the n minus 1. That is our expression for the nth term of the geometric sequence. And again, we could check our work. The correct expression will verify the given information. If I plug in 2 for n, I have to get out 12, which I do. If I plug in 5 for n, I have to get out 3 over 16, which I also do. So we know that we have the correct answer. All right, one more example here. 2 terms of a geometric sequence are given. Find the missing term. We have a3 is equal to 16/3. a7 is equal to 256 divided by 243. And we want to find a subscript 6, the 6th term of the sequence. Well, anytime we want to find one of the particular terms of a sequence, the best thing to do is find the expression for the nth term. Again, once we have the expression for the nth term, we can plug in any value for n that we want. We can get any of the terms of our sequence. So let's go ahead and find it. And because it's a geometric sequence, we know it's going to come in the form an equals a1 r raised to the n minus 1. Well, just as we did before, we're going to have to set up a system of equations. The third term in the sequence is 16/3. This means that when we plug in 3 for n, we must get out 16 over 3. In other words, 16 over 3 has to equal a1 times r raised to the 3 minus 1. The seventh term in the sequence is 256 divided by 243. This means that when we plug in 7 for n, we must get out 256 over 43. So we're plugging in 7 for n, we're getting out 256 over 43. That gives us 256 over 43 equals a1r raised to the 7 minus 1. And again, now we have a system of equations, 2 equations and 2 unknowns. Well, solve the system by substitution. Let's isolate a1 in the first equation. To isolate a1, we would divide by r squared. a1 is equal to 16 divided by 3r squared. I can now substitute that in for a1 into the second equation. 256 divided by 243 is equal to 16 over 3r squared times r to the 6th power. Now, we can, again, simplify r to the 6th divided by r squared here. I am dividing exponential quantities with like bases. We subtract the exponents. 6 minus 2 would leave me with r to the fourth power. 256 over 243 is equal to 16 over 3r to the fourth. Again, we need to isolate r. To get r on its own, we need to divide by 16 thirds. That's the same thing as multiplying by 3 over 16. That gives us 16 over 81 is equal to r to the fourth power. Make sure you guys are comfortable dealing with these fractions in your calculator, okay? Plug this division or multiplication, however you do it, into your calculator. And don't forget, use that math frac option to give you the simplified form of the fraction. So we have 16 over 81 is equal to r to the fourth power. And in order to solve for r, we must take the fourth root, and taking the fourth root is the same thing as raising to the 1/4 power. Now, one thing to be careful of, whenever we take an even root, there are going to be positive and negative solutions that we need to account for. And so when we take the fourth root of 16 over 81, we end up with r is equal to plus or minus 2 divided by 3. All right, so there are actually two different common ratios, one being positive 2/3 and one being negative 2/3, that meet the given criteria. Okay, now that we know r, we can back substitute into this equation here to solve for a1. Now notice, because we have r squared here in the denominator, it doesn't matter if we plug in positive 2/3 or negative 2/3, we're going to get out the exact same value. A1 is equal to 16 divided by 3 times the quantity, plus or minus 2/3 squared. All right, so make sure when you go, if you're going to plug this in your calculator, have this entire denominator in parentheses, all right? Again, you don't necessarily need to plug in positive 2/3 and negative 2/3 because they're going to end up giving you the same value when you square it. And we get our solution for a subscript 1. A1 is equal to 12. So now that we have A1 and R, we can plug them into our expression to give us the nth term. In this case, we actually have two solutions. An is equal to 12 times 2/3 raised to the n minus 1, or an is equal to 12 times negative 2/3 raised to the n minus 1. All right, so there's actually two expressions for the nth term that satisfy both of these given pieces of information. Well, now that we have our expressions for the nth term, we need to find the sixth term. And how do we find the sixth term? We plug in 6 for n. And you would simply just plug in 6 for n into each one of these equations. Plugging in 6 for n gives us a subscript 6 is equal to 128 over 81, or a subscript 6 is equal to negative 128 over 81. Notice that we get opposite answers. So the one where our common ratio is positive, our outputs are always going to be positive. All the terms of our sequence are all positive. With this one, where our common ratio is negative, the terms of the sequence are going to alternate sign. Every even term, this is an even term, the sixth term, is going to be negative. Every odd term would be positive. And that's why A3 and A7 are both positive. All right, so there you have geometric sequences.